Let's look at motion in one dimension, acceleration in one dimension. Motion along a straight line is referred to as one-dimensional motion. It can be forward and back, it can be left and right, it can be up and down, but it is along a straight line. If a person is walking down a straight hallway, that's an example of one-dimensional horizontal motion. If an elevator is moving up and down through an elevator shaft, it can only move along a straight line. That is one-dimensional motion. An acorn falling from a tree, that's also one-dimensional motion. Here are two examples of one-dimensional motion. Look carefully at them. How are they different from each other? Well, if we look at the horizontally moving ball, we see that if we draw a line from one image to the next, we keep drawing these lines, we're going to see that each of these lines is equal in length to every other line. That tells us that this ball is rolling at a constant velocity. How do we know that? Because these images are taken at equal time intervals. So if we see that each of these lines is equal length, then that means that at each time interval, the ball travels the same distance. Remember, velocity is the displacement over time, the displacement traveled over time. So if we see the same displacement over the same time, repeated time and time again, that's constant velocity. If you look carefully at the vertically falling object, you're going to see that the lines gradually get longer and longer and longer. That tells us that with each time interval, the ball travels farther in the same period of time than it did in the previous time interval of equal size. So this is what we call accelerated motion. This is one example of accelerated motion or accelerated velocity. We can say that this ball is speeding up as it falls. When an object is in motion, its position is always changing. That's a definition of an object in motion. It's a change in position over a change in time, or displacement over time. If we graph position versus time, then if we had an object that was sitting still, it would have the same position over that period of time. We'd have a horizontal slope. The slope would be equal to 0. That means no motion. If the object is moving, if it's moving in a positive direction, then we would see a positive slope. And so the displacement or the position is increasing over time. If it's moving in a negative direction, we'd see a negative slope where the position is decreasing over time. Now, acceleration is a change in velocity. When we see straight lines like this, then that tells us that there's a constant velocity. Well, with acceleration, we wouldn't see straight lines. We would see curves or possibly angles because acceleration is a change in velocity. Remember, velocity is the change in position over the change in time, and this is the same as the slope of the graph. Acceleration is a vector quantity. That means that it has both magnitude and direction. You can have positive acceleration, you can have negative acceleration. So just as velocity is the rate of displacement, delta x over delta t, acceleration is the rate of change of velocity. Okay, acceleration is delta v over delta t. So if I drew a graph showing velocity versus time, then the slope of this graph would be the acceleration. Here we go. Okay, the acceleration is the change in velocity over the change in time. This is This is a graph of something that is speeding up at a constant acceleration. Okay, motion is everywhere. Okay, things are moving all the time. And so we're used to things moving. But in physics, we need to describe that motion. We need to explain it. We need to be able to predict it. And we need to understand how forces affect changes in motion. We have an idea of patterns of motion, what patterns are normal and what motion is out of the ordinary. If you remember our investigative phenomenon, we saw an example of a ski jumper that traveled through a path like that. Parabolic path is what we called it. Well, the picture that we saw only showed the ski jumper going this far. But because we are used to patterns, we're used to identifying patterns, we were able to predict that the ski jumper would continue to follow this parabolic path until he landed on the ground. If you were to watch a soccer game, if you saw somebody kick the ball, you would know where the ball was going or in which direction it was going and what kind of path it might follow. So what pattern do you see in the motion of the falling billiards ball in the earlier image? Let's look at it again. Okay, here we see that the ball is falling straight down. It's following a one-dimensional path. However, as I showed you on the last image, here we can see it a bit larger. The ball from one point to the next, each distance, even though each time interval is the same, each distance, each displacement is longer than the last. That's the pattern we see. The pattern we see is that a falling object speeds up at a constant rate as it falls. If a ball's rolling to the right at a constant velocity, and then hits a spring, it's going to slow down when it hits the spring. It will slow down and stop, and then it will bounce back in the opposite direction. So we're going to look at what this looks like. And we're going to try to describe the acceleration of the ball before, during, and after hitting the spring. And I want you to think about, how does the spring affect the velocity and the acceleration of the ball? If we look at this image, we see equal time intervals, right? Time equals 0, 1, 2, 3, 4, 5, 6, 7, 8. When the ball is first rolling, in fact, throughout the whole first few images, we see that the acceleration equals 0. Acceleration equals 0. Acceleration equals 0. That means that the ball is moving at a constant speed, constant velocity, and a constant velocity. And what is that velocity? It's equal to v. Okay, v. Well, when the ball hits the spring, the spring slows it down. The spring slows it down. So what does that mean? How do we describe that? We can say that its velocity is decreasing. The velocity is decreasing. And we can say that the acceleration is in which direction? The acceleration, we no longer have a 0 acceleration. We can say the acceleration is to the left. Okay, so when you have acceleration and velocity, notice the acceleration here and the velocity are in opposite directions. When you have velocity in one direction and acceleration in the other direction, then that means that the object is slowing down. And we can see that if we look at these arrows, right? This arrow is longer, and then this arrow is shorter. And then what happens at t equals 4? What's happening here? Well, that's when we don't see any velocity. So at t equals 4, the ball comes to a complete stop. V equals 0. But notice the acceleration is still to the left. Okay, so acceleration is left. And that's kind of something a lot of people don't think about, is that an object that's not moving and has zero velocity can still have an acceleration, because the acceleration is what's going to change the velocity. It's only for an instant. It's for just an instant in time. It has a velocity of 0 and an acceleration to the left. But that acceleration is necessary because when the spring expands, it pushes the ball to the left, and the ball accelerates. It speeds up to the left. So here we see velocity. I guess if we say that the velocity in t equals 0 through 3, if we say that the right is the positive direction, let's say right is positive and left is negative. So here on t equals 0, t equals 1, t equals 2, we can say that the velocity in that case, is positive. So now that the direction has changed, we can say that the velocity is negative. Or we can say velocity is less than 0. It's going to be a negative number. And the acceleration is still to the left. So the acceleration is still to the left. But if we also know that positive is to the right, negative to the left, we can also say that the acceleration, we can say that the acceleration is negative because the acceleration is to the left. Now, notice here we see that the acceleration and velocity are in the same direction. When acceleration and velocity are in the same direction, that means that the object is speeding up. So when the spring expands, it speeds up the ball and sends it flying off in the left direction. But now, notice velocity is constant. Acceleration is 0 because now it has no force pushing it to speed up or slow down. That's this scenario that we see here. This can be graphed just like this. Okay, so this graph shows the exact same thing. Here we see this slope from, here from t equals 0 to right about the time it hits the spring, which is, right about here, right? Or maybe here. That's a constant, that's a straight line. Okay, so if we look at position over time, then the slope is the velocity. The velocity is a change in position over a change in time. Rise over run. So the velocity is constant until, this point right here when the ball hits the spring, and then the velocity starts decreasing. And we can see that the slope is decreasing until it gets down to like this kind of a slope. That was a terrible line. I'm sorry about that. But we can see that the slope is constant, and then it starts decreasing, and then it continues to decrease until we have a negative slope. And a negative slope means what? It means a negative velocity. So what's happening is that the acceleration is 0 up until the ball hits the spring, and then the acceleration is negative. Acceleration is less than 0 because it is pushing the ball to the left.